So, good evening. So, welcome to Stochastic Process class. Today's lecture 14. We have two more lectures to go. Okay. So, yeah. So today we'll recap. We were doing everything about DTMC. Mm, So the last class we saw strong Markov. In the last to last class we saw strong Markov property, stopping time, and then different classes of recurrent and transients. Mm, In the previous class, we are calculating what is the mean number of returns to state. So if a state is recurrent, then it is infinity. If it is transient, it is infinity. Then we gave some theorems on DTMC. What happens if the state space is transient, and what happens to the conditional distribution of the number of times that the state is hit. If it is a transient state, then you can find the probability distribution for the state to be hit m number of times. If it is a recurrent state, the probability to hit m number of times goes to 0, because if it is a recurrent state, then with probability 1, you'll hit the state infinite number of times. So the distribution would be 0 at all points. It will be just 1 at infinity. Using this conditional probability, we found the expected number of times you hit a state. If it is a transient state, then you get a formula of fjj by 1 minus fjj, where fjj is the probability of you hitting j conditioned on um, the fact that you have started from j. So if that is if j is transient. If j is recurrent, then the expected number of times you hit the state j is infinite. Okay, this is clear. Yeah. Then we discussed about community classes and class properties. So we saw what does it mean. So uh, if I if there exists some positive probability of going from state I to state j in any number of steps, then we say that I is reachable from j. And if both are reachable from both the states, so that means that if j is reachable from I and if I is reachable from j, then we say that the I and j communicate with each other. And we also saw that this communication is also an equivalence relation. So which means that uh, communication supports reflexive. So every state communicates with itself, and it is symmetric. So if a state communicates with other state, then the other state also communicates with this state, and it's transitive. So if A communicates with B and B communicates with C, then A communicates with C. So using this, we saw an example for where different community class partition this state space. So if two states can never belong to uh, two different classes. One state can never belong to two different classes. So if a state belongs to a class, then all the states that communicate with that given state belongs to a single class. And if you have a state which belongs to some other class, then all the states communicating with that class belongs to that communicating class. Now you can't have a state communicating from one class to another. So you have two different. So it's a disjoint set. So you have partitions of the state space based on this community class. Now you say community class is closed if you started in the closed community class, then you'll always stay in the community class. You'll never get out of the community class. Then that type of community class is known as a closed community class. And yeah. So here we saw an example where the states 1 and 2 are one community class, 3 and 4 are one community class. But 1 and 2 is not closed community class, because you can see with some positive probability you can go from 2 to 3. But there is no way once you go to 3, you come back to 2 and 1 and 2. So even if you start at 1, 2, eventually with some positive probability you will reach 3, 4, and once you hit 3, 4 states, you'll stay evident indefinitely in 3 and 4 states. So 3 and 4 is a closed communicating class, where C2 is a closed communicating class, C1 is not a closed communicating class. Next, we saw about irreducibility. So if there is only one communicating class, then we say that the transition matrix is the Markov chain is irreducible. We gave some examples. And trivially, if a Markov chain is irreducible, then it is because it has only one closed class, one communicating class, irreducibility. So if you start in that, you'll have to start in the class because there is no other communicating class. So you will with probability 1 you will start in the class. With probability 1 you'll always stay in the class. That is how the Markov process is defined. So if Markov chain is irreducible, then that class is also closed. It's also closed Markov chain. So then we saw some theorems about null recurrent, positive recurrent. So what we saw was so the frequency of visiting the states finite time, that is 0 if J is null recurrent, and it is greater than 0. It's positive if it is positive recurrent. So recurrence also has two classes. So that is if J is recurrent, then the limit that you see there, that tends to infinity. If it is null recurrent, it also tends to infinity, but slower than n. If it is positive recurrent, it tends to infinity proportional to the rate at which it tends to infinity. So the rate at which it tends to infinity, if it is null recurrent, the rate is slower. If it is positive recurrent, it is faster. So the frequency of visiting states in null recurrent is 0, but in positive recurrent, it's positive. Then we state that we saw the theorem where we say that if one community class, if one of the state is transient, then everything is transient. All the states are transient. If one of the state is null recurrent, all the states are null recurrent. One of the state is positive recurrent, then all the states are positive recurrent. Then last class we also saw about positive recurrence and invariant probability vector. So here we gave out a theorem which states that so if a DTMC is irreducible, positive recurrent, then there exists a probability distribution such that pi equal to pi p. So what pi equal to pi p? This pi is known as invariant distribution. What does it mean is if you are starting initial distribution, you're starting with that pi. So then the distribution, because of the property of the transition probabilities, the probability of you being in some state at nth step would always be pi. The probability of you finding yourself in some state in the nth or n plus 1 step doesn't change. So this you can see from the expression that pi equal to pi p. Now you multiply p on both sides. So multiply p, since p is a matrix and pi is a vector. So you need to be careful. If you write multiply p on both sides, then you see that pi p is equal to pi p square, but pi p is equal to pi. So you get pi equal to pi p square. So the second step transition probability. So the probability of you finding in some state after 2 steps, that is also pi. Similarly, if you keep on continuing this recursive reaction, pi p power n is also pi. So probability of yourself finding in some state, say after n steps, remains the same. That is why it is known as invariant distribution. Invariant distribution is different from steady state distributions. So in invariant distributions, what happens is if you start using this distribution will continue throughout all the steps. Steady state distribution is if you started with any initial distribution, eventually you will reach uh, a particular distribution which will be invariant. But the condition is that you can start from any other probability distribution. It need not be the invariant distribution. Now, For it to be a steady state distribution, it needs to be invariant because steady state distribution eventually will come. Eventually lead pi equal to pi p. So steady state distributions need to satisfy the invariance property, but invariant distributions, all invariant distributions need not be a steady state, because if you start at some other distribution, there is no guarantee that you will end up in this invariant distributions, given that you have started at some other distribution. Given that you have started this invariant distribution, you'll always stay in the invariant distribution. That is the thing. But we were talking about invariant distributions, and we gave some remarks on it. So one of the remarks was we were trying to find the left eigenvector for P. P is a stochastic matrix, so the right so it has an eigenvalue of 1. Because it has an eigenvalue of 1, uh, the vector with all ones is an eigenvector for the trash matrix, but that is a right eigenvector. We are trying to find the left eigenvector for P. Mm. And second remark was all the n-step probabilities remain the same. And the third remark was this is what is invariant. You'll have some invariant distribution. This shows that the process is stationary because the probability that of you finding at some state doesn't change with respect to time. And then it was that if P is irreducible, pi equal to pi p, then if some of the initial distributions are positive, then all the states would be positive. We also showed this. Then we saw that if it is positive recurrent, you can normalize that and to get a unique pi. If it is null recurrent, then there might exist an invariant distribution, but it will not be unique. Then we did the proof, and the theorem that if a DTMC is irreducible and positive recurrent, there exists a probability distribution pi such that pi equal to pi. And we also showed that pi is unique. These two things we did last time. So today we'll do an example. An example is of the discrete time. Markov chain, but we'll be doing m/m/1 cube. So I'll tell you what this mm1 stands for. But before that, let me go into let me give an explanation of the process. What this cube means. So first we'll consider a single server cube. Right. So what does this mean? You have a server which serves. This server example could be anything. So it could be a shop where they process customers. So customers come in line by line, they serve the customer leaves. So it could be a tea shop. Suppose it's a tea shop. Customers come. There is only one counter. So you have one counter. So there's only one server. So customers come, they place their order, and they wait for their order to be received. And the server makes the order, gives it to the customer leaves. Right. Then this is customer one. Customer one. Now customer two comes. Customer two might come even when the customer one is there. So he'll be in line. So customer one, customer two. And then now customer two will get to place his order. Since each could order some different things, the time that it takes for to serve customer one could be different from customer two. Customer one could have some order which is very long, so it would take a long time for him to serve. Customer two could have an order which is very short, so it could take a short time for him to serve. And then once they serve customer two, he leaves. Similarly, this goes on. So people keep on coming, they keep on getting served, and they go away. So once a customer reaches this part, this is known as HOL, head of line. So once you reach the head of line, then only you'll be served. So you need to wait. So there are waiting times associated here where customer comes, he waits in the queue, he reaches the head of the line. Once he reaches the head of the line, he places order. The server uh, tries to serve him the order, and then he gets his service, and then he goes away. So the waiting time is basically how the queuing time plus the serving time. So there's a queuing wait time, there's serving wait time. Once the service is done, he goes away. Okay. So this is a basic single server queue type of uh, model. Now the example here is this will all be done in discrete time. So what do I mean when I say that this all will be done in discrete time is, so your time axis t, and you have 0, t1, t2, t3, t4, and so on. So these need not be 1 second, 2 second, 3 seconds. So because they're discrete values of time, they'll have equal spacing between them, but there could be some unit. So this is t0 is 0. T1 could be 1 into some delta time. T2 would be 2 into some delta time. T3 would be 3 into some delta time. This delta time is, yeah, your to fix. It's like it could be anything, could be fine. But there are multiple of the natural numbers, if that is clear. Okay. So now uh, what does what does it mean when I say that this model evolves in discrete time, right? So when I say this model evolves in discrete time, it means that at T1, customer arrives or customer leaves. Both, all the things happen. And then you update the system, like how many people are there in the queue, who went away, who is the new head show, like, and everything. So at each discrete time event, the arrivals and departures of the customer occur in this queue. So that that is what I mean when I say that we are modeling the MM1 single server queue in discrete time. So all the arrivals and departures occur at discrete times. Okay, so now let the number of customer in queue at time Tn. I'm not writing nth dimension because it's a discrete. So Tn would be some n into delta. That delta is what you get to choose depending on what you're modeling. Right. So this is equal. This is Xn. Okay, this is what we're interested in. Right. So at each time instant, how many numbers of people have arrived? And we'll also make the assumption that X0 equal to 0. You're starting off with 0 customers. So when the shop opens, there are no customers, and then at first time, some point comes. Okay. So first we'll define an successive inter-arrival times. So now by inter-arrival times, I mean, suppose here one customer arrives, right? And here one customer arrives. And somewhere here another customer arrives, right? So these are the inter-arrival times. Okay. Successive inter-arrival times will define it with integer valued random variable. Why integer valued? Because the whole model is in discrete. So you'll say after how many discrete time steps did the customer arrive. So here it would be just two, because after two time steps, a new customer arrives. Here again, it would be two. No, this would be some three or five. So it is a random variable which takes integer number of time steps, random variables. And since there are many arrivals, this would be a sequence of random variables. And they are I. We'll make the assumption that they're I. And that sequence I'll denote it with AN. Right. So now I also need to give the probability distribution of the random variable. So the probability distribution of random variables, probability AI equal to K is equal to 1 minus lambda power 1 minus K minus 1 into lambda for K greater than or equal to 1. Right. So here the parameter lambda lies between 0 and 1. And so some important points to note is that inter-arrival time is at least one. So you have to wait for at least one slot for one arrival. And at each slot, there can be only one arrival. So inter-arrival time is at least one. And at each instant, because of the inter-arrival time being at least one, because of that, at each instant, there can be at most one arrival. Okay. Also, we see that this distribution, inter-arrival time distribution, is geometric. So basically the continuous counterpart for exponential, right? Geometric also shows the memorylessness property, but it is a discrete transform. So why is it geometric? I'll just give a small this thing. So what this tells is, suppose the inter-arrival time is k, right? That means that for k minus 1 in time slots, there were no arrivals. Then there was an arrival, because the arrival at each time slot is independent of each other. So at the first time slot, nothing happened. So 1 minus lambda. Second time dot, no arrival came. So 1 minus lambda. Because they are independent, 1 minus lambda to 1 minus lambda, you multiply it over k minus 1 times, because for k minus 1 times nothing happened. And then you get an arrival at the kth time instant. So that is with probability lambda. So lambda here gives the probability of u of the arrival in between a time slot, right? Probability of an arrival in a time slot, in one time slot, right? And since that is geometric, this looks like Bernoulli distribution. So you have a lambda probability with which either a packet arrives or it doesn't arrive, right? So if you actually think clearly, uh, in the continuous counterpart, you'll get the Poisson and exponential. In the discrete counterpart, you'll get Bernoulli and geometric. So the same thing when we discuss about continuous time Markov chain, you'll see that we are talking of exponential waiting times and Poisson number of state changes or state jumps, those kind of things, right? Okay, so one more assumption is customers are indexed by their order of arrival. So you know which customers has arrived first and which customers has arrived second. And the customers wait in the service buffer in first come first some basis. So customers are indexed in the order of their arrival. And they are addressed or they are scheduled first come first serve basis. So whoever customer has a lower index will get served first, then the other. So okay, so now suppose there is a customer which enters service. It takes BI time steps for it to service. Okay, so now we talked about inter-arrival times. We'll talk about service times. So let type customer take BI amount of time steps, time slots to be served, right? So now BI also is a sequence of random variable because each customer would have different orders and each would take different amount of time. These are also IID because each customer itself, they are independent to each other. Now, okay, so yeah, so these are also IID with a common distribution. Now that distribution is given by probability of BI equal to K equal to 1 minus mu K minus 1 mu, right? For K greater than or equal to 1. And similarly for 0 less than mu less than 1, right? So from here again we get the same points. That we noted is it takes at least one time interval to serve a customer, right? And notice that again, the service distribution is geometric. Okay. So since now we have described what the interarrival times are and what the service times are, we are interested in the queue lengths, the total number of people that are in the queue at time n. So xn, these are known as queue lengths. Right. Okay, so before we use the sequence of ANs and BNs, because now we know that these both are geometric distributed, we'll use something simple, a much more simpler distributions to characterize Xn, right? So for that, we'll define two independent Bernoulli sequences. Alpha n and beta n. So these both are Bernoulli sequences. So what does it mean? They are IID, and they're independent among themselves. So alpha n equal to 1 with probability lambda and 0 with probability 1 minus lambda. Beta n equal to 1 probability mu and 0 with probability 1 minus mu. Right, these are the two Bernoulli. So now what these two means physically is if if at Tn alpha n equal to 1, this implies that an arrival has occurred. So now the interarrival times would be geometric distribution because you have with this probability arriving and with this probability no arriving. So the distribution of interarrival times would be, if you know that uh, uh, interarrival time is k, then 1 minus lambda whole power k minus 1 into lambda would be the distribution, which would be geometric distribution. So when the Q is so now suppose Q is non-empty. So what does this mean is xn is not equal to 0, right? Then there is a bit at HOL. So now that HOL position would depart in the next time instant m, when delta m equal to 1 implies departure has occurred, right? And say for some m, for some k or tk, say the queue is empty, right? Which implies xk equal to 0. If then delta k equal to 1, because there's nothing to send, this is just ignored, right? So this model, this ignored part and these all inverse correctly models the service type sequences. Because geometric distribution has memorylessness, so when a customer arrives to an empty queue owing to the memorylessness property of the geometric distribution, the number of steps until the next time instant Tm at which delta m equal to 1 is still geometrically distributed independent of anything else. So now we have a Bernoulli arrival process and a Bernoulli virtual service process. These both alphas end and beta ends. The service process we call, okay. So this is Bernoulli arrival process, and this is Bernoulli virtual service process. This is known as virtual because if the queue is 0, and even if the service process gives you a 1, it doesn't serve. It only serves if the queue is non-empty. So the analogy to this in the continuous time counterpart will have Poisson processes. The CTMC will study in the next class. Uh, so this whole setup is known as the MM1Q. So this whole setup is known as the MM1Q, right? So the first M refers to the arrival process. So this is the arrival process. This is the service process. And this is the number of servers, right? Okay. So since we have formulated it as a Bernoulli arrival process and Bernoulli virtual service process, so the parameters lambda is basically the arrival rate and nu is basically the service. Here M means memoryless. The arrival inter-arrival times are memoryless, and the service inter-service times are memoryless. Then hence, because they're discrete, they are geometric. These M could also stand for Markovian and Markovian. M Markovian. Okay, so the recursion in which the queue length happens, the most important thing is xn plus 1. So you want to know the number of customers in the next time instant. Xn minus delta n plus 1 plus minus alpha n plus 1. Okay, so So what does this mean is, so in the next dimension, the number of people. Okay, so first I'll write what this means. So this can be written as max of 0 comma xn minus delta n plus 1 minus alpha n plus 1. So basically, if I write a plus, this means it is max of 0 comma a. Okay. This is the most important equation, the recursive equation. Okay. So what does this mean is, so delta n plus 1 is number of bits, number of customers that have left the service in between n and n plus 1 time instant. So suppose there were 5 people in the line in xn, and suppose one has left. So now 5 minus 1, this would be 4. Max of 0 comma 4, it is 4. And now suppose no arrivals have come. So minus 0. Then xn plus 1 would be 0, right? Now suppose both, there is a service and there is an arrival. So suppose there were 5 before, delta n plus 1 is 1, minus 1. Again, this would be 4. But now, okay, this is plus. Now one arrival has happened. So you're subtracting the number of people that have received service and went away in that time slot, and you're adding the number of people, new customers that have come into the queue. So this is the new customers in queue. This is the customers who have left service. Okay. Right. So if both of them are 1, 1 has left, 1 has, then it will remain the same 5. Okay. Now you would think that why is this max 0 this necessary? So what happens if there are no customers in queue, xn equal to 0? Then suppose delta n plus 1 gets 1, then this goes to minus 1. But because of the max term, max 0 comma minus 1, so this would, sorry, yeah. So since it is max 0 comma minus 1 plus, now this is alpha n plus 1. This would be 0 or 1, right? So this goes to, this will be 0. So even if delta n plus 1 is minus 1, if there are nothing to serve in xn, uh, this would remain 0. Now it would increment if alpha n is 1, then x plus 1 would go. So if a new customer has come, then only it will go to 1. If not, it will go to 0. It will remain at 0. Okay. So this equation is the recursion equation where uh, you can uh, see that how the queue length updates at each time instant. Okay. So uh, take a closer look at this equation. So xn plus 1 equal to max of 0 comma xn minus delta n plus 1. Delta n plus 1 gives you a number of customers that have left the time slot. At max, it can be only 1 for our case. And plus alpha n plus 1. Alpha n plus 1 is the number of new customers that arrived in the queue in that small time slot. Okay. Okay. Now, from the recursion, we can see that probability xn plus 1 equal to j, condition not x0 equal to I0, x1 equal to I1, and so on, xn equal to I, right? This is equal to probability of sorry, probability of xn plus 1 can be written as xn minus delta n plus 1 plus plus alpha n plus 1 equal to j, condition dot x0 equal to I, and so on, xn equal to I, I0, I1, I2. Now you can see that since you only need xn, you don't need x0, x1 and all, according to the recursion. This is basically xn minus delta n plus 1 plus alpha n plus 1 equal to j, conditioned on xn equal to I. If you just know that xn equal to I, then you'll know what is the probability that xn of xn plus 1. You no need to know x0, x and all. So given the history, you just need the previous time instant. So this I call it as Pij. And this shows that the MM1 queue, the total number of customers in the queue follow a Markov, is a Markov chain, right? And the sequence alpha and delta n do not depend on any past evolution, because alpha and delta n are just some Bernoulli IID random sequences. This establishes that the process xn is a DTMC on all the all the positive integers, right? So now the transition probabilities. The transition probabilities are V2, right? Okay, so we'll write the transition probabilities Pij equal to. So this is basically transition probability. Okay, so uh, you can't jump. So if only an arrival occurs, you jump the xn plus 1 is plus 1, right? If only if both arrival and departure occurs, you stay at this previous at the state which you are in. If only a departure occurs, you go back one step. You can't go back two steps because two departures can't occur the same slot. You can't go forward two steps because two arrivals can't occur at the same spot. So it is 0, right? If j does not belong to I minus 1 plus or I plus 1, right? So I plus 1, if you are in ith state, right? So j could be either I plus 1, right? Or I minus 1. Okay, there is a probability of it being I also. Does not belong to I plus 1, and max of I minus 1 and 0. Because if I is 1, no, if I is 0, then you can't go to minus 1. You have to go to positive 1. So that I minus 1 has a plus and I plus 1, and you can stay in the same state. Okay. Now with probability 1 minus lambda, right? So if you are at state 0 and you come back at state 0, that means no arrival has occurred, right? And even if departure has occurred, it doesn't, you are getting it is getting ignored, so it is 1 minus lambda. Okay, lambda, if I equal to 0, j equal to 1. Okay. The 0 has the special touch probabilities. After that, it is mu into 1 minus lambda. So for I greater than or equal to 1 and j equal to. So what has happened here is here departure has happened, right? arrival has not happened. So it is I minus 1, and it is lambda into 1 minus mu for I greater than 1 and j equal to I plus 1, right? So here arrival has happened, right? And then you have 1 minus mu into 1 minus lambda plus lambda into 1 minus mu. So this is for I greater than or equal to 1 and j equal to 1. So both has happened. So now if you expand this, you can see that 1 minus mu lambda plus lambda minus lambda mu. Okay, cancel. 1 minus mu plus lambda. Oh, sorry. Okay, so hmm, this is basically uh, arrival also has happened, and arrival also has happened, and a departure also has happened. So uh, j is equal to the state has not changed. Okay, so first we have shown that MM1, the model that we have done, is a Markov chain, right? We have written down the recursive equation of how the number of customers in a queue uh, evolve using this recursion. Then we wrote down the transition probabilities. Now we'll write down the transition probability diagram. Right. So transition probability diagram, it has all the positive integer states. So 0, 1, 2, so on, right? So going from 0 to 0. So it means no arrival has happened, 1 minus lambda. Going from 0 to 1 means one arrival has happened, lambda. Going from lambda 1 to 0, it means one departure has happened, but no arrival has happened, right? Staying in 1 to 1, we'll come to it. But first, let me write down 1 to 2. 1 to 2, arrival has happened, no departure. 1 to 2, arrival has happened, no departure. 2 to 1, departure has happened, no arrival, right? And staying in 2 to 2, these all probabilities would be 1 minus mu into 1 minus lambda into 1 minus mu. Okay. Similarly, if you have the state n minus 1, n, n plus 1, right? Here also you'll see that all the about going back probabilities would be mu into 1 minus lambda. Coming in probabilities would be lambda into 1 minus mu. Going back probabilities would be mu into 1 minus lambda. Coming probability would be lambda into 1 minus mu. Same. And there'll be self loops. These self loops all would have this problem. And this is a transition probability diagram. Now we'll analyze this DTMC. So yeah, it is pretty clear that it is a closed commuting class, because with some probability you can go from anywhere to anywhere, right? It's irreducible because, okay, you take state 0. If you want to go to state n, you just travel, you have positive probability in n steps to go from 0 to n. If you want to go from n to 0, also you have a positive probability to go from n to 0. So going from anywhere to anywhere, all the class communicate with each other, right? So all the states communicate with each other. Because all the states communicate with each other, so it is just one single communicating class. Because it is a communicating class, single communicating class, the DTMC irreducible. So DTMC is irreducible, right? And since it is irreducible, it has a single closed communicating class, right? It it is actually yeah. Now, okay, the next thing that we're interested in is the Q stable. So what do you mean by when I say that Q stable is does eventually the Q blow up to infinity? So mm, does xn go to infinity as n tends to infinity with probability 1? So the problem with this is that suppose you have modeled a customer shop with those parameters. Now for some parameters you see this event happening, right? So what does this mean is, as time goes on, the number of persons in the queue would keep on accumulating and they would reach infinity. So the shop that is serving using these parameters would have such a long line that yeah, he'll not be able to serve those many people who are coming in. So that is a problem. So stability here means the xn stays a finite number. The number of people in the queue is a finite. It doesn't blow off to infinity. Okay. So basically what it means that if the DTMC is transient, right? If it is transient, so now suppose I take state 2, and if the state 2 is transient, so okay, um, let let state 2 is transient, right? If state 2 is transient, then all states are transient. If all states are transient, then xn blows up to infinity, because it will hit only to a finite number of times. It will hit n only a finite number of times, and it will keep on increasing and increasing and increasing and increasing. It will never come. So if the state is transient, this implication is due to irreducibility, right? So let state 2 be recurrent. If it is recurrent, all states are recurrent, right? But here also, the blowing up, it will depend on what type of recurrence it is. If it is a positive recurrent, then the mean frequency of visiting states is not 0. It will be some positive thing. If it is null recurrent, it is 0. And then again, it will blow up to infinity. So first we'll look at the conditions under which this Q-length DTMC is positive recurrent. Okay. So okay, so we'll be applying the theorem that we proved last class. So which says that if you have a DTMC which is reducible, it is positive recurrent if there exists a probability vector pi such that pi p equal to pi equal to pi p, and they are positive, right? So yeah. So now we will try to find a probability vector pi such that pi equal to pi p, and then that will imply that in the DTMC is we'll get the conditions for which the DTMC is positive recurrent. Okay, so first we'll write so pi equal to pi p. Now, okay, the transient matrix. I'll just write the transient matrix so that it will be clear. Is basically 0 to 0 is 1 minus lambda. 0 to 1 is lambda. Rest of them are zeros. These zeros goes off to infinity, right? Next is 1 to 0 is mu 1 minus lambda. So this is mu 1 minus lambda. 1 to 1 is that whole thing of 1 minus mu into 1 minus lambda minus lambda into 1 minus mu, right? And the third one is lambda into 1 minus mu and all 0. Okay. Only this is 0, but this would become mu into 1 minus lambda, and this would become 1 minus mu into 1 minus lambda minus lambda into 1 minus mu. So become lambda into 1 minus mu. This all goes to 0. So the same number keeps on going in the diagonal. Same numbers, diagonal above and diagonal below. Okay. So this is the P matrix, right? P into pi P. Pi equal to pi P, right? So now pi P, the first equation. So this is P. We have pi. We'll have pi 0, so on, equal to, we'll have pi 0, so on, right? So the first equation would be pi 0 equal to pi 0 into 1 minus lambda plus pi 1 into mu into 1 minus lambda, right? Other everything's are 0. Okay, 0. Again, you'll get something, 0. This is clear, right? So now if you simplify this, you'll get, so bring pi 0 all to one side. Pi 0 lambda equal to pi 1 into 1 minus lambda mu. This will get pi 1 equal to pi 0 by 1 minus mu into lambda by 1 minus lambda by mu by 1 minus mu, right? So next, this is what you got from the first. Next, pi 1. You'll get pi, so pi 1 is this, pi 1 equal to pi 1 into this second column. So that will be, so this will be pi 0 so on transpose equal to pi 0 so on transpose is this. So pi 1 equal to pi 0 lambda plus pi 1 into 1 minus lambda minus 1 minus mu lambda plus pi 2 into 1 minus lambda. But you know pi 1 equal to pi 0 by 1 minus mu. You know this equation, right? If you substitute this here, you get pi 2 equal to pi 1 lambda into 1 minus lambda by mu into 1 minus lambda. So for any n, you'll get the recursion that pi n equal to lambda into 1 minus lambda by mu into 1 minus mu. This is mu. Pi n minus 1. Okay, so for the pi p equal to pi equal to pi p, you'll see that if you complete this recursions, you'll get pi n equal to lambda by 1 minus lambda by mu by, these are pi 1 minus mu whole power n pi 0 by 1 minus mu, because we're replacing. So pi n minus 1 could be replaced with the same thing into pi n minus 2. Pi n minus 2 will same thing into pi n minus 3, and you go up till pi 0, right? You'll get this. So, but we are seeking a probability vector. So we want to make sure that summation I greater than or equal to 0 pi I is equal to 1, right? So this you'll see that you'll have it only if pi 0 into 1 plus 1 by 1 minus mu summation I equal to 1 to infinity lambda by 1 minus lambda by mu by 1 minus mu whole power I equal to 1. Now you can see that this is an infinite sum. The sum for this is finite if lambda is less than mu, and if lambda is less than mu, let us assume. Okay, so first let us assume that lambda is less than. Then this sum is finite. Then we get pi 0 into 1 plus 1 by 1 minus mu into 1 by 1 minus lambda by mu into 1 minus mu by 1 minus lambda minus 1. Which simplifies to pi 0 into 1 plus lambda by mu minus lambda equal to 1, or pi 0 equal to 1 minus rho, where I'm taking rho to be lambda by mu, right? Since we have assumed that lambda is less than mu, which implies rho is less than 1, right? So now we have pi 0 equal to 1 minus rho, pi n equal to rho n into 1 minus rho into 1 minus mu by 1 minus lambda whole power n 1 by 1 minus mu. So now we have gotten probability vector for which, so now probability vector which sums up to 1 uh, and also follows pi equal to pi p. So this implies that the DTMC is positive recurrent. Because the DTMC is positive recurrent, it is stable if the assumption that we got was for the summation to be finite, lambda less than mu. So lambda less than mu implies the arrival rate should be less than service rate, which intuitively makes sense. If the arrival rate is less than service rate, then the queue will not blow up to infinity. If more people are arriving with more rate than the rate at which you're serving, the queue will eventually blow up to infinity, right? So for lambda by mu greater than or equal to 1, that is rho greater than or equal to 1, uh, the summation won't converge and there'll be no solution of pi equal to pi p, right? So it will be only true if lambda is less than mu only, you'll get a solution of pi equal to pi p. Uh, right. So yeah. So the the conclusions that we get from our DTMC is, so if you have a DTMC of xns with which are q length gradation, so rho is equal to lambda by mu, then if rho is less than 1, xn is positive recurrent. Right? If rho equal to 1, xn is null recurrent. Rho is greater than 1, xn is transient. Right? So yeah, this was the analysis for the MM1Q, which today we first showed that it is a discrete time Markov chain. We wrote the recursive equation. From the recursive equation, we wrote the transition probabilities. From the transition probabilities, we showed the how to run the transition probability diagram. From the transition probability diagram, we found whether the states are transients or recurrent or positive recurrent or null recurrent, and under what conditions those three will be based on when does there exist a probability vector that, such that it follows pi equal to pi t. We wrote down the equations and we found the condition for which the Q is steady. In the next class, I might not take it on Wednesday. I might take it a bit early. I'll inform you guys by mail when will I take the next class. And next class might also be a 3 hour long class because I'll complete CTMC in one sitting for those 3 hours, and those 16 lectures will be done. So yeah. So for today we have completed DTMC. Discrete time Markov chains are done. We have also shown a full-fledged example of DTMC. In the next class, we'll be dealing with continuous time Markov chains. So I'll stop recording. Yes.